This lesson concerns subspaces of topological spaces. A subspace is a topological space in its own right, but it's also contained in a larger topological space. In this lesson, we'll look at a definition of a subspace, and then we'll have some examples. Let's look at a definition of a subspace of a topological space. Given a topological space X with topology tau and a subset S of X, the subspace topology on S is defined by this topology tau sub S, and it equals S intersected with each open set in the topology for the containing topological space. So in words, a subset of S is open in the subspace topology if and only if it is the intersection of S with an open set in the containing topological space X. If S is equipped with the subspace topology, then it's a topological space in its own right and is called a subspace of X and represented as S comma tau sub S, which is the notation I found in Wikipedia and at least one other book. I'm not crazy about this because it doesn't take into account the name of the containing topological space. Maybe it should be called S sub X and then T sub S, but in any event, that's the notation I've seen. Subsets of topological spaces are assumed to be equipped with the subspace topology unless otherwise stated. So I'll make that assumption as I go forward. Then we have these definitions here. The sets V, an element of our subspace topology, are relatively open subsets of S. That's the terminology used, relatively open. The reason for that is they may be open in the subspace, but not in the containing topology. So that's the reason for that. And then the sets complement of V, where V is relatively open, are relatively closed subsets of S. So we'll see another way of identifying relatively closed subsets of a subspace in a theorem on the next slide. Using the definition of an open set in a subspace, we can derive a similar condition for a set to be closed in a subspace. And we have that stated here in this theorem. Let S be a subspace of a topological space. A subset A of S is relatively closed, what we defined in the previous slide, in S, if and only if A is the intersection of S and a closed subset of X. So we need to prove this in both directions. Let's first assume A is relatively closed, in S. So we start with that, and then that implies that the complement of A is relatively open in S, which implies there exists an open subset B of X such that the intersection of B with S equals a complement of A. So I drew that down here. We have S, we have A, which is relatively closed. Then we have the complement of A within S. And since the complement of A is by definition open, there's some set B in our topological space, some open set B in our topological space, whose intersection with S equals the complement of A. But then you can see from this diagram that A now is the intersection of S and the closed subset X slash B, in other words, the complement of B. So complement of B is everything outside of B, and that intersection with S, gives you A. And this is, of course, a closed set since it's a complement of an open set. So that gives us the theorem in the forward direction. Then going in the other direction, I don't have a diagram, but hopefully you can follow it. Going in the other direction, we have that A is the intersection of S and a closed subset of X, which I call T here. Then the complement of A is the intersection of S and the open subset, the complement of T of X. Thus, by definition, the complement of A is relatively open in S, which means that A is relatively closed also by definition. Okay, so we have, I think, an easier way of determining a set to be closed by this part of the theorem here. If A is closed if it's the intersection of a closed subset from our topological space with our subspace. And we'll see that in some of the examples that follow. Let's look at a few examples. The subspace topology of natural numbers as a subspace of the real numbers induces a discrete topology, meaning that the set of all subsets of natural numbers, each one of those is an open set in this subspace. And we can see that by looking at a few examples. Let's say we just want the natural number 1. Then we could take the open set of real numbers about 1, not including any other natural numbers. And when we intersect that with the natural numbers, we just get 1. Excuse me. If we wanted to set 1 and 5, we wanted to show 1 and 5 was an open set in this topology, we could take the real numbers in an open set about 1, only including 1 and no other natural numbers, and the same about 5. Take the union of these two open sets, it's open, intersect that with the natural numbers, and we just get 1 and 5. And we can do that for any subset of the natural numbers. You just need to take a bunch of small open sets about each one of the natural numbers you're interested in, and then take the union, intersect that with the natural numbers, and you'll get the subset that you're looking for. A second example is a little bit more complicated. Let's take the rational numbers as a subspace of the real numbers. That's not the discrete topology. For example, if you take 0, there's no set in R, no open set in R that you can intersect with the rational numbers to get just 0, because the rationals are dense in the real numbers, and there's nothing, no matter how close you get about 0 with an open set of real numbers, you're never going to just get the intersection to be 0 alone. For A, B being rational numbers, the interval AB is open because you can intersect that with the real interval AB and the rationals, and then the intersection would just be the rationals from A to B. And then you could do the same thing for the closed interval about AB consisting of rationals. You can intersect the closed set from A to B of reals with the rationals, and then you would get this set here, the closed set from A to B consisting only of rational numbers. Now you can't do that if A and B are irrational. In that case, the A and B is both open and closed, so you're not able to get one being open and then the other one being closed here. You get both open and closed. And that's because when you intersect the real interval, either open from A to B or closed from A to B with the rational numbers, you're still going to get this open interval A to B consisting of rationals, so that you get this being both open and closed. And the last example is if we just take the set 0, 1 as a subspace of R, that's both open and closed because a subspace is a topological space. And as we know, all topological spaces have the empty set in the space itself, at least, as open sets. However, as a subset of R, clearly 0, 1 is a closed set. So here's an example of why we needed to use the term relative open and relative closed. A few more examples. Consider the set 0, 1 closed, union 2 to 3 closed. Take the union of these and let that be our subspace S. Then each one of these components of our subspace S is open. For example, we can take the interval minus 0.1 to 1.1, which is an open set in R, and intersect it with this union, and what we get is 0, 1. So by definition, 0, 1 is an open set. And then we could do something similar for 2, 3. We could have taken, say, the open set 1.9 and 3.1 up to 3.1 and intersect that with this. We'll just get 2, 3. So that proves that each one of these components of our subspace are open. But we could have also taken even 0, 1. We could have intersect the closed interval 0, 1 from R with this union here, and we would just get 0, 1. So that would imply from our theorem 2 slides back that 0, 1 is closed, and we could do the same thing for 2, 3. So each one of these components in our subspace are both open and closed. And this is known as a disconnected space for obvious reasons. We have a gap in here. And we have another similar example, not a disconnected space, but similar in terms of a subset from the real numbers. So let S be the closed open interval 0 to 1. Then the closed interval, open interval 0 to 1/2 is open in S, because we could take an open set, say minus 1 to plus 1 from R, and intersect it with S, and we'll get this set here. So since it's the result of an intersection with an open set in the containing topological space, this is open. But of course it's neither open nor closed in R. And then I gave a different example here in writing, but it goes along the same idea of what I just said. Then we have another subset, closed interval 1/2 to 1. That's closed in S, because we could take, for example, the closed interval 0 to 3/2 from R and intersect it with S, and we'll get this set here. But this is not open. We can't find any open set in R, so that when we intersect it with S, we get this here. Right? There's no. We could try going open set 1/2 to 1, but then we miss the point 1/2. So there's no open set in R that when you intersect it with S, you get this set here. So this is not open. And then we know this already. S, being a subspace of the real numbers, is both open and closed. Okay, so that's it for subspaces. We'll continue with continuous functions as defined in a topological space in the next lesson.